Hello class. Today we're going to continue with titrations. There are several different types of titrations that you come across in this chapter. There's the titrations that were already introduced in chapter 4, which was strong acid with strong base, and we do recap that briefly. But you can also have titrations that involve a strong acid with a weak base, a strong base with a weak acid. You can have also solutions where you have a buffer forming, and we're going to explore various ramifications of each one of those possibilities. Let's start first of all with a titration with a strong acid and a strong base, just to review what happens. Whenever you have a titration, what you're doing is you're using a solution containing a known concentration of base, for example, and slowly adding it to an acid of unknown concentration in order to determine the concentration of the latter, or vice versa. You could have a known acid concentration added to an unknown base concentration, and what you do is trying to achieve equivalence. And equivalence is, in the case of a strong acid and a strong base, when the pH equals 7. There are indicators that you can put in the solution. You add a couple drops that will change color when the pH is approaching 7. And for most purposes, that's enough to determine the equivalence point, especially when the pH is close to 7. When you do titrations at a pH close to 7, the equivalence point tends to be quite dramatic because you're dealing with concentrations that are very low. And it takes a very little concentration change to make a large change in color. So for example, when you do a phenolphthalein titration, phenolphthalein turns turns color at pH 7. It turns a bright pink, and then if you add too much, it becomes magenta. So you know when you've overshot because it gets a little too dark. Anyway, this is on practice example on page 734 of your text. It's a strong acid with a strong base. Nitric acid, a strong acid with potassium hydroxide, which is a strong base, 0.1 molar each one. In this case, they've added 24.9 milliliters of the solution of nitric acid to 25 milliliters of the potassium hydroxide. So you're just before the equivalence point, so there's still a very slight excess of potassium hydroxide. The excess is 0.1 milliliter of extra potassium hydroxide. And the total volume of the solution is almost 50 milliliters. You're 0.1 milliliter short. The total volume is 49.9 milliliters. So we can then calculate the concentration of hydroxide ions using equations that we've used before. So the number of moles of solute contained in a solution is equal to the molarity of the solution times the volume of solution in liters. So the molarity is 0.1 moles per liter. There is 0.1 of a milliliter, which is 0.1 of a thousandth of a liter. A 1 milliliter is a thousandth of a liter. You have 0.1 of a milliliter, so it's 0.1 over 1,000. Multiply all those numbers together, you get 1.0 times 10 to the minus 5 moles of hydroxide in the solution, which has a total volume of 49.9 milliliters. So the hydroxide concentration is going to be the number of moles divided by the volume in liters, and you get a concentration of 2.004 times 10 to the minus 4 molar. Take the negative log of that, and it'll give you the pOH, which is equal to 3.7, rounds off to 3.7. So the pH is 14 minus the pOH, so you get a pH of 10.3. So you see that even a 0.1 milliliter excess already pushes the pH up to 10.3. 100 orders of, 1,000 orders of magnitude more than 10 to the negative 7. So you're already looking at a substantial pH change. So the pH changes are pretty quick when you're close to neutral because they involve very small changes in concentration of either hydroxide or protons. Be aware that in a titration between a strong acid and a strong base, at equivalence, the pHs are going to equal to 7. If you titrate a strong acid with a weak base, your pH is going to be less than 7. Why is that happening? Because when you titrate a weak base, once you achieve equivalence, you've created now from the weak base you've protonated it. So when you protonate a weak base, you create a weak acid. So that's the conjugate acid of the weak base. So the conjugate acid will affect the pH after you reach equivalence, so the pH will tend to be less than 7. If, on the other hand, you were to titrate a strong base with a weak acid, the pH is going to be greater than 7 for the same reasons, because now you've deprotonated a weak acid. The resulting counterion, the conjugate base, is going to make the pH greater than 7 by abstracting a proton from water. We'll see specific examples of that later. So let's now do an example where we're going to titrate a weak acid with a strong base. This is on page 737 of your text. Incidentally, tonight you should watch parts 7, 8, and 9 of the acids and bases playlist. And also the last video on that playlist is entitled How to Calculate pH at the Equivalence Point. I think I'm going to do exactly the same question. So you'll get a recap. It's just going to be me, except 8 years ago. So on page 737 it says, calculate the pH in the solution formed by adding 10 milliliters of 0.05 molar sodium hydroxide to 40 milliliters of 0.025 molar benzoic acid. Ka of benzoic acid is 6.3 times 10 to the minus 5. B, calculate the pH in the solution formed by adding 10 milliliters of 0.1 molar hydrochloric acid to 20 milliliters. Oh, okay, that's another question altogether. All right, so let's start with part A. I'm going to erase so we can do it at the top of the board. So-called board. Does not erase very well at all. Takes a considerable amount of elbow grease to erase this board. I think I'm going to go to Staples today, buy another one. I left my other one in Edmonton. My wife can use it, so just invest in get another one. Okay, that's good enough for now. So let's begin by showing the reaction. You have sodium hydroxide reacting with benzoic acid, which looks like this. The result is benzoate anion, where the ionizable proton has come off, and you get water, right? You don't need that part. The part we're interested in is this part of the equation. So you have 10 milliliters of sodium hydroxide, which is 0.50 molar. So if we calculate that number of moles, N is equal to MV, the molarity is 0.050 moles per liter times 10 1,000ths of a liter, and what you get is 5.0 times 10 to the minus 4 moles of sodium hydroxide. On this part of the equation, you have 40 milliliters of benzoic acid, and it has a 0.0250 molarity. it has a Ka of 6.3 times 10 to the negative 5. So therefore its pKa is equal to 4.20. So you take the log, negative log of that number, you'll get the 4.20. Significance of pKa, it is the pH at which half of the acid is ionized. So if you take a sample of benzoic acid and you put it in a solution where the pH is 4.2, half of it will be ionized. That is what pKa means. Using the equation again, N is equal to mV, molarity of 0.0250 mole per liter, times a volume of 41 thousandths of a liter, gives you 1.0 times 10 to the negative 3 moles of benzoic acid. What do they say? Adding 10 milliliters of 0.05 to 40 milliliters. So 5.04, because this is a strong base titrating a weak acid, you're going to get the same number of moles of benzoate anion forming as there are moles of the strong base. So you're going to get 5.0 times 10 to the minus 4 moles of benzoate anion produced in a total volume of 50 milliliters, because you have 10 plus the 40. So what does that give you as a concentration? Let's call it A minus, the benzoate anion, just for ease. We'll call this HA, the protonated form. So you get 5.0 times 10 to the negative 4 moles divided by 0.05 of a liter. It gives you a concentration of 1.00 times 10 to the negative 2 molar for the benzoate anion. The acid is in excess. So what can we say? It's going to be 1.0 times 10 to the minus 3 moles of the acid minus minus 5.0 times 10 to the minus 4 of the base, and you get 5.0 times 10 to the minus 4 moles of the protonated acid still present. It's not acid, it's not acetic, it's called HA. So the concentration of the acid, of the still undissociated acid, is going to be 5.0 times 10 to the minus 4 moles in 0.50 liters of solution. So what you get is 1.0 times 10 to the minus 2 molar. If we use the Henderson-Hasselbalch equation, we can find the pH. Remember that Henderson-Hasselbalch equation is pH is equal to the pKa plus the log of the conjugate base concentration over the acid concentration. pKa of benzoic acid is 4.2, and the two concentrations are 1.0 times 10 to the minus 2 and 1.0 times 10 to the minus 2. So basically it's the log of 1, which is 0. So you're going to get 4.2 plus 0. So the pH is equal to 4.2 according to the Henderson-Hasselbalch equation. The key here is to calculate the proper concentrations of the acid and its conjugate base. Classic error that students commit is they forget to add the total volume, okay? The total volume is produced by adding adding the titrant to the original sample. So you get a total volume. You're mixing two aqueous solutions. Total volume has to be 50 mLs. If you forget to do that when you calculate your concentrations, you're going to put the wrong number in the denominator, and everything after that's going to be wrong. Okay? So try 737B. On that same practice exercise, try to do part B. Doesn't hurt for you to read ahead too. And don't forget to watch the playlists I indicated, parts 7, 8, and 9 of the acids and bases playlist, and also the last video on that playlist, which is titled How to Calculate pH at the Equivalence Point, and I will see you tomorrow.